Hi, welcome to Simulated Engineering. So today we will see like the use case of this constant stress. What is this constant stress and in which scenario we need to use the constant stresses and why to even use it and why to even bother it about this. So firstly let's back to the constant stresses. Like constant stress like is any type of stress which will be during the assembly of the component. Maybe like suppose there is a real life example like uh, during the assembly there are fewer nuts, bolted joints are there and it needs to be tightened. So there will be a preload stresses will be generated in the component. So this might be the one use case of the constant stresses where constant stress will be applicable in this case. Then if you apply the variable load and try to calculate the fatigue and you are not considering the constant stresses, then your fatigue life will be more, and in reality your fatigue life will be maybe 1000 or maybe 2000 or maybe 10,000 cycles less than whatever you will be calculating without the constant stresses, because the constant stresses are mostly in most of the scenario are tensile in nature, and that will lessen your fatigue life. So we need to introduce the constant stresses wherever it is applicable. So bolt pretension is one of the scenario where constant stress is applicable. The second might be your press fit analysis. During the assembly, if something we are press fitting it or something interference is there and we are press fitting it, then there will be stresses will be generated during the assembly itself. That's it. Some kind of residual stresses will be generated, and when you apply the and when it is subjected to fluctuating loading, then these stresses will play a severe role in your fatigue life, in the assessment of your fatigue life. And third, and maybe example will be like the screen example. It will have a certain uh, constant stress due to its self weight itself. So the weight from uh, the weight from here to here will be try to bend this crane, and you will have a significant tensile loading in this in the upper fiber, and this will be a constant stresses. This will be termed as a constant stress. This will be always be acting on the crane, and whenever you are pulling load and dropping it, then this cycle, this constant stress will be added to those. So this is one of the example of constant stresses. There are other examples also. So sometimes it is very critical to consider the constant stress in your fatigue assessment. So that is why there is an option in FEMFAT to use constant stress. So we will see one of the examples, live examples using abacus as a solver. So before starting here, let's go to the whatever the solved ODBs I solved it earlier. So this ODB, like this is the first load case where I am just constraining it here in one to in all DOFs, and I'm applying a load here. So its animation is like this. This will be my positive load, and I will use the scale factor to use the negative load. I will use the scale factor in FEMFAT to use it as a negative load also. Means upper and lower I will use the same ODB. If you don't know what is scale factor or how to use this scale factor, just watch this video which is at the top end. Now coming to what I solved for the constant stress. I will show you what I solved, and that is a very realistic load case. Uh, Let me open this ODB. It is opened. So what I am doing here is uh, I will play the animation, and you can see like it is deflecting in this direction, in the downward direction. Actually what happens in here is I am constraining it here and I am applying the load here. I am assuming like uh, there is some self weight, sorry, there is a small weight I'm putting it here. So the weight of it I'm just applying as a load, and that will be my constant stress in this beam, and my pulsating load, sorry, my alternating load will be in this direction, will be in longitudinal direction. That is just, this will be my longitudinal load. Okay, so I will use this in FEMFAT. So let's start. So firstly is, we all know that is, I need to uh, just set the directory. I will set this directory first. So change directory, no, and you can put this, and you can just erase this. Okay, so let's start now. Yeah, so I will load my Abacus INP as I have solved in Abacus. You can even use Nastran, or you can use ANSYS, or you can use OptiStruct or any other solver, and you can solve in your fatigue. After getting the stresses, you can solve in FEMFAT. Then once this is loaded, you can go to groups, and you can just go to what is the component name. We need to check the component name auto 1. So let's get auto 1 and this, and just add this stress data. Now here I'll show you, like in the upper load case I will use post load, so it is loaded. In lower load case also I will use post load. Okay, and I will use the factor here, which will change this stresses to negative. Just I will put -1, apply. So it is changed to negative, close it, and in constant stress I will use my whatever the load which is causing the bending of the beam. So this is my constant stress. Okay, then I will go to material. I will define a material of steel which is having a, ultimate strength of 500 MPa. Okay, I will press OK, and then I will go to load spectra. I will use new here. This steps you guys already know. Then in node characteristics, you need to put auto, then this FE500, and this, as it is a machined part, I will use 60 microns as my surface roughness. In the influence factor, then you need to check the surface roughness option, and you need to also check the constant stresses options. Then in the blast you can use mean plus amplitude unfavorable sequencing effect. If you don't know what is this, you can watch this video which is here. Then uh, you can go to analysis factor, and you can just switch on absolute. This global is fine. Output is, I need to change it to hypermesh DMA file, and then report. Then analyze, I will go to auto, and I will go to check input data, is whether my input data is correct or not. So it looks okay. Then I will click on analyze. So once analysis is done, you can use either the FEMFAT visualizer, or you can use the hyperview itself. Yeah, so we will check our fatigue life now. So for this, you just need to load the DMA file, and yeah, you will get your fatigue life here. So 1 by damage is nothing but your fatigue. So just apply, and you need to reverse this because we are more interested in minimum fatigue life, and that should be the red color. Okay, and is all together red. Yeah, so it's all together red, and I'm expecting like you will get your least fatigue life in here, because due to bending you will have the mean stresses piling means sorry the constant stresses piling up here, and your pulsating fatigue, your pulsating load will give you the stresses everywhere, because that is a normal stress. And so we will just put one value here. Let's see what is the value. We will mark one node here. Okay, let's uh, calculate the amplitude stresses and the mean stress. So mean stress I will just put for uh, 1052 node, and it is 165 MPa mean stress, and your it's approx 165 MPa, and your amplitude stress is 141, 142. So your mean stress is 165.2 MPa, and your amplitude stress is, what is the value we got? 141.7 MPa. So we will try to calculate this values, and we will further we can further check it whether we have done the fatigue, whether the software has done the fatigue analysis correctly or not. So we will go to our model, and this is by the way the node number 1052, and we will go to signed one misses. Just roughly I am calculating it. This is not the exact calculation, but give us it will give the idea. And yeah, so signed one misses, you need to use corner data and advanced average, as FEMFAT is using corner data with advanced average. And so I need to annotate uh, 1052 stress, 1052 nodal stress. Okay, 1052, and so uh, it is so this is by hyperview. So it is one somewhere 142, okay, MPa during your longitudinal load, positive load. Okay, and what about this one? So again we will do signed one misses, advanced average, corner data on. Okay, and we will try to calculate this node. Sorry, this is advanced average should be switched on, and we will try to calculate node number 1052. Sorry, nodal contour I want 281.9, 281.9 MPa during constant stress. By the way, these are all positive. These both values are positive. So now how to calculate your mean stress? So we want to calculate the mean and amplitude stresses by using hand calculations to further verify our FEMFAT results. So here is the calculated amplitude stress. So amplitude stress is nothing but upper stress minus lower stress divided by 2. So upper stress is like longitudinal positive load, that is 142, and plus constant stress which is positive of 281.9, minus then bracket. Then lower stress is, we have used the scale factor to make this as negative in lower stress. So it is minus 142 plus of this value divide by 2. The It comes out to be 142, which is nearly equal to 141.7. So that means that is amplitude stress is correct. And one more thing to notice here is amplitude stress is independent of your constant stresses. So whatever constant stress is, it will never increase or decrease your amplitude stress, but it will have a significant increase or decrease in the mean stresses. So we will see next. So if you see that mean stress is nothing but your upper stress plus lower stress divided by 2. So upper stress, if you calculate it, it is 142 plus of 281.9, and lower stress is same here. So it comes out to be 139.9 and 423.2. This is just, and I will, if you calculate this, you will not get 164.95, but you need to take into mind like these are just the stresses from linear material properties. We have used the plast option. So we have used the plast option. We have used the plast option. So this stress, if you see this is the yield strength of the material. So this stress is well above 284.5. This is well above yield limit. So we need to convert it into Newber stress. That's what FEMFAT plast is doing. So if you convert into Newber stress through hand calculation, it is coming out around to be 190. And if you calculate that, your mean stress is somewhere around 165, which is nearly equal to mean stress of FEMFAT stresses. So we have calculated the amplitude and mean stress from the ODB abacus stresses, and we have again evaluated the FAMFAD mean and amplitude, and both are nearly equal. That means whatever we are doing, it is correct only. And second thing, one may ask like why you have not used Newber correction method here in amplitude stresses. Even if I use Newber correction here, whatever the value this will make, the same value this will make, and it comes out to be 142 only, because this and this will get cancelled, and again your amplitude stresses will be equal to this value only. So this is how you can calculate amplitude and mean stresses. And even if you have doubt, if you are unable to calculate the Newber stresses, what you can do here is, uh, I will tell you what you can do here is, you can simply switch off this option called blast. Then your results will be not be correct, but your mean stress and amplitude stress calculation will be quite simple, because whatever the, it will not convert the linear stresses into Newber stresses, and whatever the calculate, your calculation will be quite simple. You don't want to convert into Newber stresses, but your fatigue life will be lot less if you are not using blast and you are using linear material properties. Thank you. Have a great day.